Thank you, Jim, for inviting me to give this presentation.
Me, by the way, it's not your meeting.
Yes, so Jim will be there in Uppsala. It's the first European photosynthesis meeting. That's what he's alluding to. So thanks for coming there also. Yes, so many of us are here to kind of study the mechanism of water oxidation. And we have heard a lot of talks. Most actually took a structural approach. They were trying to resolve the structure of photosystem 2 in different estates and measure things and to kind of deduce the mechanism in this way. There is a possibility to approach this in a different way, to kind of look where the substrates are. And you just alluded to that in the question to Junko. It's very difficult to have techniques to actually measure the substrate where it is, or measure some property of the substrate. And so there are many techniques to see water molecules. One is X-ray spectroscopy. Another one is EPR. If you label the water with 17O, for example, you can see couplings to water molecules that are close by. Or you can use FTIR. But all these techniques that actually don't distinguish between substrate water, the water that will finally form the O bond, and other water molecules, structural water molecules or whatever. So in my presentation, I want to present you one technique that I developed while I was postdoc in Tom Wojcinski's lab in Australia that is applying membrane inlet mass spectrometry to probe the substrate water. I will go more into this technique during my presentation and explain it, but before I can do that, I have to mention a sad fact. While Victor was talking, I received the email from Fred Chow that Tom passed away.
Thomas?
Tom Wojcinski.
Oh, really?
Yeah.
Yes.
So I need to mention that I can't do that.
Well, you should. And he was a fabulous guy, and he did what you're going to describe are very impressive experiments, and he was behind that, wasn't he?
Well, yeah, I was developing it in his lab, yes.
So what he did with you was absolutely outstanding. And anyway, let you carry on.
Yeah. Okay, so having said that, I don't need to say very much here. It was covered already. So water splitting is catalyzed by this cluster of 4 manganese ions and calcium ion here. That is embedded into a protein matrix, and you see in blue lots of water molecules around it. And I also like to point out the chloride that was mentioned briefly by Victor that is close to the cluster. This cluster undergoes a redox state changes, can attain 4 or 5 different redox states, and then water splitting occurs. So the dark stable state is as one state, so if you give 1, 2, 3 flashes, then water is split. And on these different states, on each transition, 1 electron is removed, except for S4 to S0. There's a chemistry occurs. And on most steps, protons are removed. So the crystal structure shows us 4 water molecules. 2 are bound to the calcium, W3 and W4, and 2 are bound to the outer manganese, one of which may be a hydroxide, W1 and W2. And so the big question is, what are the substrate water molecules, which will form the O bond? And then in addition, we need to consider also oxo bridges as possible substrates or water from the outside. So things that have been proposed would be the coupling of W1 and W2. Another thing that can be easily imagined is the nucleophilic attack from W3 to W2. Something similar one could imagine between W3 and O5. Or as was explained by Per Sigban, and I had early proposal also on this, that there could be a coupling mechanism. Water comes in, and there could be this O bond formation between a terminal water molecule and the O5 oxo bridge. Now, how to probe this? And this is the technique that I mentioned, this membrane inlet mass spectrometry. So here you have a water solution that is separated from the vacuum in the mass spectrometer just by a thin membrane. It's a thin silicon membrane, so that is gas permeable. And so the gas molecules will penetrate into the vacuum while the water stays behind. The little bit of water vapor that comes through can be frozen out, and then the molecules are ionized, the gas molecules, and separated in a magnetic sector field. So if I then couple this to a custom-made cell, we can here have the PS2 sample, we can illuminate it, put it by the flashes into different S states, and then we have a fast rapid injection system here where we can inject the O18 water at different times, for example, before the S3 state. So we use 2 flashes to set the sample from the S1 into S3, then we inject O18, and then after different times we give a third flash that produces the first pulse of oxygen, and then we can sample the isotopic composition of that oxygen, thereby directly monitoring which of the substrate have been exchanged. So how much of the label of the substrate comes in here. So by this method we actually, while we exchange many water molecules, but the rates that we obtain are directly reporting on the 2 substrates. So if we do that now, we see 2 kinetics. If we look at the 34 oxygen, that means one of the substrate has been exchanged, the other one not. So then we see a fast phase and a slower phase. And if we look at the 36 peak, we just see the slower kinetics. So that directly showed that both substrate water molecules actually are bound in the S3 state to the manganese cluster, and they are bound in different chemical environments because they exchange with different rates. One can now vary the sequence of pre-flashes and flashes afterwards, and by that probe also the exchange in the S2 state, in this one state, in the S0 state. And here you see some examples of these kind of measurements. You see all the S states show the same behavior, the 2-phase kinetics and for the 34 and the 1-phase kinetic for the 36. And one can see also that we can nicely resolve the fast water exchange in the S3 state and in the S2 state. So both substrate waters are actually bound in both states, in S2 and S3. We can't resolve it in S1 and S0. My suspicion is it's also there. It's just that the mixing time is too slow, so we can't see it. We can also see for the slow kinetics that it actually changes the rate with S state. So it's slow and relatively slow in the S1 state. It's speeding up to the S2 state. And then it's getting slower again or remains the same. That depends on which species we are looking at in the S3 state. So if we summarize up to here, we can say that the 2 substrate molecules are bound in different ways to the manganese cluster in all the S states. WS is bound in all the S states, WF at least in S2 and S3. Water enters. The water that has been shown to enter during the S2 to S3 transition thus cannot be a substrate water in this cycle. It can be in this later in the second cycle, but not in that cycle, according to these measurements. But there are also questions. For example, why does the water exchange rate actually gets faster if you oxidize a cluster from S1 to S2? Normally, we would expect you oxidize a cluster, the rate should get slower rather than faster. So that's a big mystery, and I think maybe the new data can elucidate that I will show you. And then what are the reasons for the species difference in the exchange rates, especially in the S3 state? Together with Alan Boussac, some time ago, we were setting out to measure also the water exchange, not only the stable states, but also in the S4 state. That means the S3 tyrosine radical state. And for that, we modified the cofactor composition, or Alan did. And so if we go to exchange both the calcium versus strontium and the chloride versus iodide, then that transition from the S3 state to the S0 state becomes very slow. It now, instead of taking 1 millisecond, it takes 45 milliseconds. So that opens the possibility to actually also do the water exchange experiment in this transient state. And if we take these exchange measurements for the S3 state, and then calculate what should be the exchange rate in the, how much exchange we should be able to observe in the S3 tyrosine radical state, we obtain these lines. So in this case, we give 3 flashes first and then vary the time before we then inject the O18 water. And because you only form an organic radical next to the cluster, one would expect the exchange rate to stay the same as in the S3 state, because on the metal side and how the water is bound, nothing should have changed in principle. But what we measure actually is that there's basically no exchange in the S3 tyrosine radical state. And that is also an experimental finding we need to take into account, and I think we understand this now. So if we summarize, in the S0 state, there's rapid exchange of the slow substrate water. These are relative rates, all normalized to the exchange rate in the S1 state. then it speeds up again to S2, and then it stays approximately the same or slows down slightly going to S3. So this is what we are trying to understand. And before I go into much more detail on that, I also like to explain these data more that I've flashed briefly before already. This is a water exchange in S3 if you exchange calcium versus strontium. So in the group of Tom Widuszynski, Henry et al. Made a nice study some time ago where they chemically exchanged calcium versus strontium. They showed that in all S states there's an increase in exchange rate if there's strontium of the slow substrate exchange rate, but in comparison to calcium. So that is basically that kind of hinted towards that the slow substrate water should be bound in some way to calcium, because it has a bigger radius, and then you expect to weaken that interaction, and that could possibly increase the exchange rate that's been observed. In contrast, there's hardly any change in the exchange rate in the fast kinetics. And these are data now on elongato samples and showing the same thing, but in this case it was not chemical exchange, but they were actually grown by Alan Boussac in these different media, especially for the calcium strontium. Now there are several proposals out at the moment that think that the fast substrate water is bound to calcium in the S2 state, but then moves to manganese 1 when going to the S3 state. So we also measured this calcium versus strontium in the S2 state, now in sample of Simerole, where we can quite nicely resolve the fast phase, and we can see that there is basically no difference in the exchange rate calcium versus strontium in the fast substrate water, making that proposal unlikely unless there is a diffusion limitation of that kinetic phase. It's not seen very well on that screen here, but there are some, in the S2 state, there's actually some deviation here from the normal single exponential rise. And we haven't published this is unpublished data because at the time we didn't understand what's going on there. But I think the new data will explain that. So, as I said, those calcium strontium data show you that the fast exchange substrate water is likely not bound to calcium, not even in the S2 state, unless the overall exchange is diffusion limited. That is something we cannot completely exclude. The slow substrate water was interpreted on the basis of these data to be bound to calcium and to manganese, because it shows both the calcium strontium dependence and it shows the S state dependence. And the most likely conclusion that I reached already around 2004 was that it could be the O5 oxygen bridge, because it's kind of connecting the two things. However, there's as an oxygen bridge based on model data is very unlikely to exchange with substrate water or with any water. So if you do water exchange, and so that needed some evidence that that can actually happen. And so I did that together with Nick Cox and Wolfgang Lubitz in Mülheim at the Max-Planck Institute. And so instead of using O18 water, we did the same experiment with using O17 water. And in this case, you have a nuclear spin on O17, so that can couple with the electron spin on the manganese cluster in the S2 state. And so first we did an experiment where we exchanged very thoroughly. So it took, the whole procedure took about 1 hour. So then you will exchange all kind of water molecules around, so maybe not only the substrate, and kind of you get this kind of envelope in this advanced DPR spectroscopy. And by comparison to model systems, this strong coupling here of the 17O with the manganese cluster can be assigned to a Mioxo bridge. And by other things I can't go into, we assigned that to be the O5 bridge. Now this of course can be many things, so we try to improve the mixing time. And the fastest to date we have, but we're working on getting faster, is 15 seconds. But if you look at this, of course, the overall enrichment is lower, so the signal is lower, but you can see that the same strong coupling is there after 15 seconds. So that shows that this is unusually fast exchanging that O5 atom, so it makes it possible to be a substrate. It could be the fast or the slow. This time resolution is not enough, or it could be just a quickly exchanging oxygen bridge, we don't know, but it's at least kinetically competent to be one of the substrates. Another way to probe it, and this was mentioned already, is to study ammonia binding. So again, with the Lubitz and Cox group, We studied that and concluded that ammonia is binding in a terminal position to the manganese 4, basically replacing the W1 water molecule. And we measured in my group then the water exchange under the same conditions, and what we see is that the fast substrate exchange rate doesn't change, while there's a small change in the slow substrate water exchange. But overall, the changes are small. So basically, what we can say is W1 is very unlikely to be a substrate water. Otherwise, we should have blocked things completely. Or
W1, not W2.
That is exchanging more quickly. And that was basically, it comes from the assignment of these peaks, because one of those, this middle peak is assigned to W2 in these measurements, and that remains more or less unchanged, or at least the data analysis of the Müller group suggested that. It's a good question. I can't give you a very precise answer, but that's the basics of it. Okay, so basically there's a difference here that is ammonia induced, and so at the time we interpret that and that is another factor of that being in trans to O5, and thereby affecting that exchange rate to some extent. That may not be the only explanation, but that was a possible explanation. Okay, so if we take those assignment of O5 being possibly the slow substrate water, we can look at the S-state cycle to see if that makes sense, to, that kind of assignment. So going from S0 to S1, there had been EXAFS data that one of the manganese distances is shrinking, and there have been EPR data to suggest things, that this is a OH in the S0 and state O5. And then one of those manganese ions would be oxidized here, and that would both together, this oxidation and the deprotonation of the O5 bridge, would explain why the exchange rate of O5 would slow down from S0 to S1. Similar from we saw that in S2 and S3 states, exchange rate is similar, and in both cases that would be the case. It's bound in a similar environment. The problem comes here, going from S1 to S2. It's not, I mean, you oxidize other manganese, you would assume that to slow down the substrate exchange of the O5, which doesn't happen. So then in 2013, when I wrote the review with Nick, and we suggested that this can be explained possibly by the second structure that is there, the G4 state structure, the high spin structure of the S2 state, having that equilibrium in some way. We had no idea exactly how, but that this would enable a faster exchange, maybe during the transition, or we didn't really know. But that was kind of the most obvious idea that this could happen. If we assume that, then we can explain this discrepancy or this problem. Possibly, but then if the exchange actually is due to that equilibrium that doesn't exist in the same way in the S3 state, the problem is why then the exchange rate is similar in these two states. And that is possibly explained by having tyrosine Z back donating electrons to the manganese cluster, in some percent of the centers to the manganese cluster, bringing it back to the S2 state where then the exchange would happen. That was a suggestion that also came from Per Siegban. And actually, if one takes those data we have from the S3 tyrosine Z radical state, where there's basically no exchange, that could explain it, because once you have the tyrosine Z radical, there can be no back donation to the structure. But there may be also another structure that would explain that, another equilibrium. So that is more maybe kind of, there could be two different equilibria that by chance give you the same exchange rate. That's what I like to say. The question now then becomes, what would be the fast substrate water? If you take the calcium-strontium results, we would suggest it's not bound to calcium unless there's a diffusion limitation, but then the next best possibility would be OH bound to manganese 1. And that also makes qualitative sense, because in S0 and S3, if you have it bound, S0 and S1, we have this W2OH bound to a manganese 3 ion, allowing a faster exchange. Then in S2 and S3, it's bound to a manganese 4 ion, where we would expect the exchange to be slower, so then it becomes detectable with our time resolution. So there's, of course, also the suggestion of so if you had it let's go back here. So if you had it here, then one would suggest maybe there would be oxygen formation in one way or another, and I had suggested that some time ago between W2 and O5 there would be a O1 formation. But now having established that water binding here, that still remains a possibility, but it could also be different. So if you assume there's a pivot mechanism or carousel mechanism, which is basically the same, of water coming in, so there's another water binding here, those things rotate, and then basically those would exchange identities. So suddenly this would be the previously fast exchanging water would now be in the bridging position, and so 5 would come out to be a terminal ligand here. If one looks at that, one would say this can't be true, because then that should exchange suddenly much faster, but if it's really due to the back donation, the exchange would actually happen here. So that way it would also be consistent. So one could live quite happily with that thing, but then it still would be nice to do more water exchange here, also on the high spin state. And that became possible when Alan Boussac contacted me, because he will give a presentation tomorrow, but it's also in his abstract, and the paper just came out, where he showed that he can actually, by changing the pH, shift that equilibrium. So at high pH, you can have almost pure G4 state, while at lower pH, in the calcium sample, you basically have pure multi-line state. So that kind of allows us to study that. And one other important finding was of Alan is that if you add ammonia at the high pH, you basically shift back the G4 state into the modified multi-line state. So this now gives us a great opportunity to study the water exchange in the two different conformers, and there's two states, so potentially giving us additional information on where the substrate water is bound. So if you look now at the 36 signal, which is the slow substrate water exchange, you can see that at pH 6, the black curve, you see the typical curve here, but if you go to pH 8.6, you see a much faster exchange. If you add ammonia to it, at 8.6, it comes back to the situation at pH 6.0. So it seems really that the water exchange depends a lot if it's in the multi-line state or in the G4 state. And now we need to try to understand that. But before we do so, we also did the experiment in the calcium and strontium samples. And there another very interesting finding comes. So basically, we also see the same difference. It's at pH 8.3 in the strontium samples, you basically see the same kinetics as in the calcium sample. But at pH 6, we now see a biphasic kinetic in the 36 peak. So it almost looks like the 34 signal, but it's not. This is a 36 signal. So there's a biphasic rise. So that shows that the water exchange is actually faster than the equilibrium between the two states, it seems to me. Otherwise, I can't really explain these data. If you look in contrast to the fast exchanging substrate water, again, there are only very small changes in that region. So basically, what we observe from these experiments is that we have a biphasic exchange rate of W slow in the strontium samples at low pH, which shows that the two states, that the G4 and the multi-line state have different exchange rates. And then there's either no interconversion between the two states, or it's slower than the fast exchanging substrate water. These two exchange rates of the slow substrate water are nearly pH independent, but relative amplitude is changing. And ammonia kind of puts the sample back to the pH 6 condition. So basically, because you convert it back, so that basically shows it's not a pH effect, but it's really connected to the structural change. That's an important part of these data. And yeah, it's not so important. So now the question comes how we put that back. 2 minutes, maybe? So I will quickly go through it. Basically, there are two ways to explain this now, and I think that's important for the discussion. So either we stick with the model that we have, that O5 is low substrate water, but then we need to find an explanation why this O5 is faster exchanging in the G4 state than in the multi-line state. That's not completely obvious to me. It's possible, I think. I think we can find an explanation, but it requires work. One would be that something similar can happen to the transition S3 state, that you have another state where there's one more water molecule bound that brings O5 out to a terminal position where it can exchange on a manganese 3 ion where it can exchange. But that is all speculation. We have no real data on that. Alternative is, if we look at this, there's obviously a big change here around on manganese 1 and manganese 4 and manganese 1. So manganese, the water bound now to manganese 4, it's now bound to manganese 3 ion. So one would expect those to exchange more rapidly than they can in the G4 state than they can in the multi-line state. So one could, since we excluded by the ammonia experiment more or less the W1 position, one could speculate that W2 is a slow substrate water instead of the fast, as I suggested in the other mechanism before. So one can, I don't probably have time to go through the whole thing, one can go through all that, see that it's consistent with ideas I proposed earlier. One thing that made me hesitant to accept that interpretation for a long time was that in the S1 state you have the slowest exchange, and there the OH is also bound to a manganese 3 ion. And you have the slowest exchange there, so that didn't make much sense to me. And also, the same, it looks very similar to binding in the S0 state to the as in the S1 state. So, but it's much faster in the S0 state than the S1 state. So that's for a while I excluded that completely. But I think there are backdoors to explain that. One would be that in the S2 state here, it's a 5-coordinate manganese 3. Well, this is a 6-coordinate manganese 3 that could affect the water exchange rate. And in addition, one could assume that there are also other states in the S1 and in the S2, and the equilibrium between this open and closed in those states could be quite different. And that could also explain the different exchange rates. I don't go through all the things, but if you go assume, I mean, one other interpretation, so that would all be consistent with nucleophilic, with radical coupling. But one could also, of course, if one brings in W2 as a slow substrate, one could also go back to nucleophilic attack and think about that. If one does so, one could, of course, that would be the obvious. But there are also some things that needs to be explained. So in this case, one would assume that there's no pivot mechanism to explain this. And also one would need to think that all the waters up here, that the must be diffusion limitation in the exchange. Otherwise, on calcium, it should exchange far too rapidly. Alternatively, if one assumes there's a pivot mechanism, so then W2 would be in the S3 state, actually in the O5 position, then it would need to be a coupling between W3 and O5 instead. Similar, when we need to have the diffusion limitation here. So I think there's maybe a paradigm shift how to explain the calcium-strontium effect on the on the exchange of the slow substrate water. It's rather equilibrium between two states, the open and the closed state, that is modulated by the exchange of calcium versus strontium. And it opens up for another site possibly being the slow substrate water. Although I have to say I still prefer O5, but one needs to be open, needs to be discussed. Thank you very much.
Johannes. So it's getting very late, but any questions now for Johannes? Yes, of course, Gary. Gary.
Yeah, you're getting some really fascinating results, but I think it's making the interpretation a lot more complicated. So,
I agree.
For example, with fast and slow exchange from two different conformations, that makes it very complicated because you've always been assuming there are two different water molecules, but they could be the same one in two different conformations.
No, that's actually not the case. No, they're the same ones.
But you did see that with the fast phase being both slow and
I mean, I didn't show. We also have experiments that actually exclude that. Actually, I have it next slide here.
No.
Okay.
No more slides.
Anyway, we have data to show that also the fast and the slow, they don't interchange. I mean, the fast, slow one
they're
doesn't
still
get
fast and slow, but
Yeah.
you have fast kinetics and slow kinetics from one water. So
It depends on the condition.
Yeah. Just a couple comments, though. I'm not sure you can necessarily make a conclusion that these exchange kinetics represent waters bound to the metal centers. I mean, you could have waters that are in a very strongly hydrogen bonding second shell environment that are slow to exchange as well.
Yes, that's what I would call the fusion limitation.
Yeah,
of an
yeah,
exchange,
so
yes.
that makes, a little bit more possibilities that you need to consider then.
I think we have.
I mean,
enough
I think I
possibilities.
always said that this is an option. It's
Yeah.
in the papers, and I just said it several times today.
Yeah, and I just, one comment about the the F3 state where all the manganese are in the +4 oxidation states. You shouldn't expect any bridging oxos to exchange at all. We showed in model complexes that they don't exchange at all in that state. And so then that was leading into the proposal that tyrosine Z could mediate the, going back to the S2 state. That's okay, but then you should have an equilibrium constant scaling the rate because there's an equilibrium
Absolutely,
constant.
that's why I was always against it. But since we now see that the exchange in the S2 state also depends on an equilibrium, and you see the species differences in these things. So I think if both are determined by an equilibrium, by chance, it can be very similar. So if it were just the same mechanism, I agree with you. It should be slower in S3. But since both are depending on different equilibria, I think it can well be the same.
It sounds like you'd have to have kind of a very precise balance of the equilibrium and the rates to make it work.
We're going to go.
We can simulate that quite nicely. So
Yeah.
We're going to go for one more question. I think we have to stop then, Per. Have you got a microphone? Don't ask me to.
I'll be
Fall over.
quick. I'm very convincing and elegant. I'm wondering about the carousel
Yeah.
motion. That the calculations done are not right, so that they can forget about that. The other thing is, do you see a reason why the veiling is interfering with this? Because it should be, to increase it a little bit, this water insertion should be significantly perturbed.
Yes, I mean we are on the process of studying mutants of the valine in the water exchange. It hasn't been completed, so I can't say.
Is it close enough in space? I mean, the veiling.
It seems like it blocks the site to manganese 1, the access. So I'm not thinking if it stays as it is, you don't have access there. I think most people agree on that. I'm not sure it can flip. Some people have looked at it. I think it can't flip. I don't know.
Manganese 1, you can rotate the veiling and get it in, but so it's close. But in the other one, where you bind to manganese 4,
Yeah.
the veiling should also be close to stopping the substrate.
Yeah. I don't know. Yeah.
Look, there is a gentleman in the audience who said to me that I should announce now that all of us have to go to our rooms and dress up. And the one gentleman in the room has got a tie on already. But I actually don't have a tie, so don't worry about it. Let's thank all the speakers.